All right, let's talk about the invisible rulebook that runs our entire physical world. I'm talking about classical mechanics. These are the fundamental rules that tell us how everything moves, from a tiny speck of dust all the way up to a galaxy. So think about this for a second. What does a speeding car, a planet orbiting the sun, and say a thrown baseball, what do they all have in common? I mean, they seem completely different, right? One's engineering, one's this cosmic dance, and the other's just a game. But here's the thing, they're all connected. And that's the secret. They all follow the exact same fundamental set of rules, a single elegant set of laws that governs all of it. So today, we're going to unpack that rule book. Okay, so where do we start? Well, to really get a handle on the rules of motion, you have to meet the main character in this whole story, force. It's the agent of all change. And at its core, it's actually that simple. A force is just a push or a pull. That's it. You see something sitting still, and then it starts moving? A force did that. You see something already moving, and it speeds up, slows down, or changes direction? Yep, a force did that too. It is literally the spark for any and all change in motion. And a force can do a whole bunch of things. I mean, think about it. It can start something moving, right? Or it can stop something that's already moving. It can make things go faster or slower. It can change the direction something is heading. And it can even change an object's shape, like when you squeeze a rubber ball. Any of these 5 things, if you see them happening, that's your clue. That's the telltale sign that a force is at work. Okay, so that's what a force is. But now we need a way to actually, talk about the motion that it creates. We need to build a vocabulary for this stuff, a kind of language of motion. Now, this is one of those things that seems simple, but it's super important. Let's talk about distance versus displacement. Imagine you get up, you walk 5 steps forward, then you turn around and walk 5 steps back. The distance you traveled is 10 steps, right? But your displacement, that's 0. Because displacement only cares about how far you are from where you started. You ended up right back where you began. So distance is the whole journey, displacement is just the straight line from A to B. And it's the exact same idea when we look at speed versus velocity. Speed is easy. It's just a number on your car's speedometer, 60 miles an hour. But velocity gives you the whole story. It's 60 miles an hour heading north. See the difference? It has both a size, the speed, and a direction. That makes it what we call a vector, and it's absolutely crucial for describing motion. Okay, and here's the last key piece of our language, acceleration. Now, most people think acceleration just means speeding up, but that's not the whole picture. Remember how velocity includes direction? Well, acceleration is any change in velocity. So yeah, hitting the gas is acceleration, but hitting the brakes is also acceleration. And here's the tricky part. Even turning a corner at a constant speed is acceleration because you're changing your direction. That's the key. Acceleration is any change that a force produces. All right, so we've got our language down. We have force, we have displacement, velocity, and acceleration. Now we can finally get to the main event, the actual rules of the game that connect all of these ideas, all thanks to the one and only Isaac Newton. So law number 1 is basically the universe's default setting, and that setting is, well, kind of lazy. Objects just want to keep doing what they're already doing. This is called inertia. So a thing at rest wants to stay at rest. A thing in motion wants to keep moving in a straight line at the same speed. It will only change what it's doing if an outside force comes along and makes it change. Okay, so if the first law says that objects resist change, the second law tells us what happens when a force does make them change. And it's pretty intuitive, actually. The bigger the force you apply, the more the object's motion changes. You push something harder, it accelerates more. Simple as that. This is the law that lets us do the math and actually predict what's going to happen. And now for the third law, which you've probably heard before. For every action, there is an equal and opposite reaction. This is so profound. It means forces always come in pairs. You can't just have one force by itself. When you push on the wall, that wall is pushing back on you with the exact same amount of force. A rocket pushes hot gas down, and that gas pushes the rocket up. It's a perfect, beautiful symmetry. And really, that second law gets summed up in probably the most famous equation in all of physics. F equals ma. Force equals mass times acceleration. This right here is the engine of the whole system. It's so powerful. It tells you everything you need to know. Got a big mass? You're going to need a big force to get it accelerating. It perfectly connects force, mass, and acceleration. Everything we've been talking about.
So, if force is what makes things change, you have to ask, what's the cost of making that change? I mean, it's not free, right? You need something to make it happen. You can think of it like a currency. In the world of physics, that currency is called energy. And the transaction, the act of spending that energy to cause motion, is called work.
Now, we use the word work all the time, but in physics, it has a very specific meaning. You could push against a brick wall with all your might for hours, feel totally exhausted, but if that wall doesn't move, you've done zero work. I'm serious. In physics, work is only done when the force you apply actually makes something move a certain distance.
And this is a perfect example. Take a ball thrown through the air. After it leaves your hand, the main force acting on it is gravity, right? It's constantly pulling it down. And since gravity is causing the ball to move downwards, gravity is doing work on the ball. It's that work, that constant transaction, that slows the ball's upward climb and eventually pulls it all the way back down to the ground.
So that brings us back to energy. What is it? Well, simply put, energy is the ability to do work. It's the currency in your pocket. And it comes in two main flavors for our purposes. You've got kinetic energy, which is the energy of a moving object, and you've got potential energy, which is stored energy just waiting to be used. Okay, so we've got forces, work, energy. Let's tie it all together and talk about the biggest, most universal force there is, the one that's acting on you right now, gravity. This was Newton's real stroke of genius. He realized that the force pulling an apple down from a tree was the exact same force that was keeping the moon locked in orbit around the Earth. It wasn't two different things. It was one universal force of attraction that exists between any two objects that have mass, anywhere in the universe. And this formula is the rule book for it. It basically says two things. One, the more massive the objects, the stronger the gravitational pull. Makes sense. But two, and this is the really cool part, the farther apart they are, the weaker the force gets. And it doesn't just get a little weaker, it drops off really fast by the square of the distance. And that little r² bit in the equation has a really cool real-world consequence you might not know about. See, the Earth isn't a perfect ball. It bulges out a bit at the equator. This means that if you're standing at the equator, you are literally farther away from the center of the Earth than if you were at the North or South Pole. So what does that mean? It means the force of gravity is a tiny bit weaker, and you actually weigh slightly less at the equator. How cool is that? And that leads us to a really important point people get mixed up all the time, the difference between mass and weight. Your mass is the amount of stuff you're made of. That doesn't change no matter where you are in the universe. But your weight? That's just the force of gravity pulling on your mass. So on the moon, your mass is exactly the same, but you weigh a whole lot less, because the moon's gravity is so much weaker. So think about where we've gone. We started with a simple idea, a push or a pull, and ended up with the universal laws that govern the entire cosmos. That's really the whole journey of physics, uncovering these deep, fundamental rules. Newton gave us this incredible rulebook for motion, which just makes you wonder, what other, even deeper rules about how the universe works are still out there, just waiting for us to find them?